When we looked at tree diagrams, we focused on making a list of all the possible outcomes in a situation. What we're going to look at today is we're going to start looking at not making a list of all the outcomes, but counting how many outcomes there would be without listing them all. Okay, so we're going to start by looking at something called a permutation. Okay, now this is different from something called a combination, which we're going to talk about later. Okay, now permutations are a particular order of elements in the set. So when we count the number of permutations, permutations are all the things that we listed in a tree diagram. So like when we looked at this problem here where we had people that we ordered, having Trey, then Vernon, then Julie, then Ray, right? Having them in that order, that is one permutation of these four people. Okay, so that's what a permutation is. It's a particular order of elements. Okay, and we're going to find the number of permutations in a set. Okay, now again, there's this other thing called combinations that we're going to look at later, and it's really important that you know the difference between the two of them. Okay, so with a permutation, you use a permutation when the order of your selection matters. Okay, so in this problem here, the order matters because if I choose Trevor first, then he sits here. But if I choose him fourth, then he sits here. So the order in which they are chosen matters because they end up sitting in a different spot. Okay, so that's what we're talking about when we say order matters. Okay, as opposed to a situation where order wouldn't matter is if I was picking three people to be on a committee together, right? So if you're picking three people for, say, student council, then it doesn't matter if you're chosen first or third, you're still going to be part of the group, right? So permutation is when order matters or when the selections are mutually independent. Okay, mutually independent, what does that mean? It means that one outcome doesn't affect the other. So in this case, these are not mutually independent because once you choose Trevor, that impacts what your choices are for the second seat, right? But when we looked at flipping a coin, these ones are mutually independent because whether you get heads or tails first, you still have heads or tails as your option the next time. Okay, so these are mutually independent. These ones are not. Okay, so that's sort of what the difference is. So you would use permutations if either the order of the selection matters, like it did in our choosing people for seats problem, or if the selections are mutually independent, they don't impact each other, like flipping a coin. Okay. All right, so having established that, right, here's some other examples. Awarding first through third place in a contest. The order matters in that case because getting first place is very different from getting third place, right? Choosing an appetizer, an entree, and a dessert from a menu. Those ones would be mutually exclusive because what your choices for your appetizer has no impact on what your entree is, right? And you have to choose just one from each category. You can't choose to take like 3 desserts. It's one per thing. Okay, so those are mutually independent of each other or mutually exclusive, same thing. Okay, so let's talk about some notation first of all. So how we write these things. So here's some notation right here, okay? So NPR is how you would say that. Okay, on your calculator, it looks like this, and we'll come back to that later, but it'll be P and then in parentheses NR. Okay, so what this stands for is it's the number of permutations of N things taken R at a time. Okay, so if you had 10 people and you were choosing 3 of them to win first through third place, you would write it as 10P3. 10 people, and you're doing a permutation of 3 of them. Okay? All right, and then this guy right here, this is a symbol. Okay, so the exclamation mark, if you've never seen that before, that is a factorial, is what that's called. So it's called a factorial, and that's how you'd say it. Okay, and what that is it is shorthand for the product of a number and every whole number less than it. Okay, so as a couple of examples, 3 factorial, that's how you'd say that. That is the same thing as multiplying 3 times 2 times 1. So it's the product of that number and every whole number less than it. Okay. 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1. Okay, so that's all that it is. It's a shorthand for multiplying out all those numbers. You have to start with a whole number to do a factorial, and it just always goes down to 1. Okay, as a side note definition for you, 0 factorial, by definition, 0 factorial is considered to be 1. Okay, it's not 0, it's 1. Okay, so that is just kind of something to keep in mind that you may need that. All right, so as we start doing these problems, right, there are a couple of different ways that you can approach doing these problems. The first way is that you can use this formula here, okay? And I'm going to kind of go through this with you and show you how to use it. But personally, I do not use it, okay? So like I'm going to show you how to use that formula during this lesson, but that's pretty much it because I just find that it works better if you kind of break it down a different way, okay? So this is what we're going to kind of look at. So think again, right? Let's go back to this. We're going to think about, well, what happened here? So when I look at this problem, what kind of went on? Well, I started with 4 different spots, right? And then from there, because I had 4 choices for the first thing, and then I had 3 choices for the next time around, right? Once I picked one of these people, there were only 3 options left in each of these kind of sections, right? So each of these 4 things split off into 3 different pieces. Well, that's what multiplication is, right? When I have 4 things and I multiply them by 3 different pieces, that's where you get 12 from. Okay, and then from there, after I'd chosen 2 things, I had 2 people left, right? So no matter what 2 I'd already chosen, there were 2 people left to pick from, right? So each of these spots split off into 2 more spots, right? So I had 4 people and I split them into, so 4 people originally, and then I had 3 choices for each of that choice, right? So I split it into 3 pieces from there. So that's 4 times 3. So there's 12. And then I took each of those and I split them into 2 sections. So I took my 4 choices here, and then 3 choices here, and 2 choices here, and I multiplied those all together, and that's where I got 24 from. Okay, and then lastly, I only had 1 option left, right? Once I picked 3 people, my last person, I only had 4 options left. So 4 options times 3 options times 2 options times 1 option gives you the total number of options. Okay, and that's what happens in a permutation. So when we look at, say, this problem right here, here's how I'm going to set this up. Okay, how many different ways can 6 people be seated in 6 chairs? So what I do is I use slots, okay? So I think to myself, how many different choices do I have to make here? Okay, I have to choose 6 things because I have 6 chairs and I have to choose 6 people to go in each of those 6 chairs, okay? Just like how in my tree diagram, I had 4 chairs, so I had to make 4 choices, right? Well, in this case, I have 6 chairs, so I need 6 choices. And I'm going to represent those 6 choices with 6 slots, I call them. Okay, where this is going to be chair number 1, this one will be chair 2, this one will be chair 3, that'll be chair 4, this will be chair 5, that'll be chair 6. Okay, so that's what my slots represent here. Okay, and I'm going to fill these with the number of options that I have to do that particular thing. So when I choose to fill chair 1, I have 6 different people, so I have 6 choices for who can go there. Okay, once I put somebody in that chair, now I only have 5 people left, right? 1 person's already sitting, so now there's 5 people standing around. So there's 5 choices for this spot. Once one of those people sits down, now I've got 4 people left milling about waiting for a chair. Okay, once I fill that spot, now there's 3 people around. So for my 4th chair, there's 3 people left who can choose it. Okay, my next chair, I've only got 2 people left. And then this guy, he's just stuck there. That one last person, he's just got to stay there, right? So now I know how many choices there are. And just like when I did my tree diagram, I had 4 choices for the first seat, 3 for the second, 2, and then 1. And if I multiply that together, that represents all the different branchings off, right? So what I'm going to do is I'm just going to multiply all of these numbers together, and that's going to tell me the total number of possible permutations of these people. Okay, so in my calculator, there's two different things you can do. You can just throw in all those numbers and multiply it and get 720. Okay, or there is a way, if you look at this and you say, hey, Miss King, that's just 6 factorial, right? There is a way that you can put that in your calculator as well. So if you can look at this and you recognize that this is 6 factorial, just like we listed here, okay, you can go in here, type in 6, go to your math menu, and then you need to go over to your probability column. So go over to the probability column. You might have an extra column in there depending on what calculator you have. And then option 4, there's your exclamation mark. So you see it says 6 factorial, and it gives me the same answer, 720. Okay, so that can be a bit of a time saver. All right, so there we go. That is how we would do that problem using the slots way. And again, that is my preferred method. That is pretty much how I always do these. Okay, but I do want to show you how to use this formula as well if that's something that you prefer. Okay, so in this case, we have 6 different people that we're putting into 6 different chairs. Okay, so when you're doing this, the 6 chairs, that is your n value because that's the number of choices that you have to choose, right? Okay, and then this number, that is your R. So you have 6 choices because you have to put 6 people, and this is how many options you have for each of those choices. That's totally backwards. I'm sorry. This one's N. This one's R. I apologize. Okay, so we have 6 people and we're putting them into 6 slots. Okay, it doesn't really make much of a difference on this particular problem, but it will in the future. So this would be 6p6. Okay, and the way this formula works is you set it up as a fraction. So n factorial, so the first number factorial, and then divided by n, which is this first number 6, minus r, which is that second number, which also happens to be 6 factorial. Okay, so that's 6 factorial divided by, obviously, 0 factorial. We already just determined that 6 factorial is 720. And remember up here we said 0 factorial is 1. So it's 720 divided by 1 or 720. And that's how that formula works. Okay, and we'll do that again as we go through and do some more examples. Okay, so let's look at the next one. So this one, we got 10 students submitting an essay in a competition. How many ways can first, second, and third place be chosen? So this is a permutation because it matters what order you're selected in. Winning first place is better than winning second place, right? So that's what makes this a permutation. So the first thing I'm going to decide is how many slots do I have? How many choices am I making? I'm not choosing 10 people. I'm choosing 3 people for first, second, and third place. So I'm going to have 3 slots that represent whoever gets first, whoever gets second, and whoever gets third. Okay, so for first place, there's 10 people who submitted it. So I have 10 choices for who wins first place. Once you win, you can't also have second place, right? So I only have 9 choices left for my second option. Okay, once you win there, you've only got 8 choices left for who gets third place. Okay, and then that is what I'm going to multiply together. So I'm going on my calculator. 10 times 9 times 8 is, hey, look, 720 again. And there we go. So there's 720 ways that you could choose those 3 people. Okay, so what would that look like if we were doing it the other way? So if we're using the formula. So in this one, right, when we set this up, n is the number of options that you have. So this 10, that would be n. So you have n different things that you could, like options that you can choose from. And the fact that there are 3 different things, that would be your R value. So this we would write as 10p3. We have 10 and we're making a permutation of 3 of them. So in my little formula, it would be 10 factorial over 10 minus 3 factorial. So that's 10 factorial over 7 factorial. Okay, so in my calculator, 10, math button, go over to probability menu. I went this way, like sideways this way, to loop around to the other side. And then I went option 4. You can either go down to 4 or just push the number 4. And divided by 7, math button, over the probability menu, option 4. And there's the 720 again. Okay. Okay, next example. So we got 4 gifts and a Yankee gift swap. All right, how many ways can presents be chosen? So in this case, right, I'm going to have 4 slots because there are 4 different choices happening, right? So this is the first choice that's happening, right? The second choice, third choice, fourth choice. Okay. So when the first present goes to be chosen, there's 4 gifts to choose from. So there are 4 options. Once it's claimed, there's 3 options left. Once one of those is claimed, there's 2 left. Once one of those is claimed, 1 left. So 4 times 3 times 2, so that's 12 times 2 is 24. So there are 24 different ways that can happen. Okay, in terms of using that formula, this would be 4p4. And it would work out to 4 factorial over 4 minus 4 factorial. So 4 factorial over 0 factorial, which is still 24. All right, next one, we got a state license plate. Okay, so state license plate has 3 letters followed by 3 digits. How many license plates are possible? Okay, so let's take a look at this one. This one's going to be a little bit more complicated, but not bad. So our license plate has 3 letters followed by 3 digits. So my choice is I'm going to have 3 letters and then 3 digits, right? So for the letters, how many letters are there in the alphabet? 26. So I have 26 choices for this letter. Okay. Once I use that, this is a license plate, right? So on a license plate, you can reuse the same letter, right? There's no like limits that you can only have one of each letter in a license plate. So unlike these, where using one in the first round dropped it in the second one, this is more like a heads or tails problem. I still have 26 choices for my next letter because you can reuse it, right? And then I have another 26 choices for the next one. The digits, so those are single digit numbers, right? You got 1 through 9 and also 0. So that's a total of 10 different options, right? So I'm going to have 10 choices for my first number, but you can reuse them, right? So you'd still have 10 choices and 10 choices for this one, right? And that is what I need to multiply together. So I'm multiplying 26 to the 3rd power times 10 to the 3rd power, which is that lovely number right there. So 17576,000. So 17 million. So if you've ever thought about how many different license plates are possible, there's a lot of them. Okay. Now, the reason why, right, coming back to this, right, I told you that I like slots better than I like formulas. And the reason why is that you can't use this formula here. Okay. Because of the fact that it's different, right? These ones you're allowed to have those repeats and those ones you're not. That's what breaks it. This formula only works if you have this you're losing an option every time feature. So this guy, we can't do it another way. It has to be done that way. And that's why I prefer the slot so much, because it really is going to help you figure out that it's different. All right, last one here. So we got teachers and a PTA meeting. So need to select 4 boys and 5 girls to sing in the meeting. They stand in a row. The boys are on the left, the girls are on the right. How many different seating arrangements are possible? Okay, so let's start by figuring out our slots. So I'm choosing 4 boys and they're standing on the left, right? Followed by 5 girls. So those are my slots. So I have 9 slots altogether. All right, when I go to choose my first boy, there are 7 boys to pick from, right? So I have 7 options when I choose the first one. Okay, once I choose him, I've only got 6 options left for the next one, and then 5 options, and then 4 options. Okay, then now I need to choose my girls, right? So for the girls, I've got 9 options for the first one, and then 8, 7, 6, 5. Okay, and that is what I'm going to multiply together to figure out my total number of options. So 7 times 6 times 5 times 4 times 9 times 8 times 7 times 6 times 5. Ta-da. Okay, so this works out to 12700,800. So 12 million. Only a few, right? 16 kids, 12 million ways to order them. And that's assuming that the boys are on one side and the girls are on the other. It's kind of crazy. Okay, so that's a little bit different. If you were going to do this problem using the formula, it's possible. But to do this one using the formula, what you'd have to do is you'd have to do it as 2 separate problems. You'd have to do kind of the boys and then the girls and then multiply them together. So you would say for the boys that you have 7 and you're doing a permutation of 4 of them. And for the girls that you have 9 and you're doing a permutation of 5 of them. And then you would multiply those 2 answers together. So you'd have to set up this formula twice and then multiply your answers together to get that final answer. So again, generally, I prefer the slot method. I just think it's a little bit easier. Okay, so that is what permutations are. And again, the key things with a permutation is that the order has to matter. Okay, and the selections have to be independent, or the selections are independent of each other. I'm sorry, one or the other. Okay, so they either have to be where the order matters or they have to be independent of each other. And that is what a permutation is.